we are here at EuCNC 2025 and 6G Summit in Poznan, Finland, where we are presenting 6G-SHINE proof of concept demos. Let's go inside and check on the booths. Thank you. And let's meet POC demonstration work package 5 leader Spelius. Hi Spelius, how are you doing?
Hello, I'm fine. How are you?
I'm good, thanks. Would you like to explain something about the 6G-SHINE and what we are doing today?
Of course. So we're here in the 6G-SHINE booth in Poznan in EuCNC, and we are presenting 3 selected proof of concept demos out of the 7 proof of concepts that we have in total in work package 5 in 6G-SHINE. So 6G-SHINE in total is targeting the subnetwork notion. Those are networks that can exist on their own without any managing policy, but they can also exist under the umbrella of a 6G network. And we are trying to identify the use cases, but also the possible technology components that can make subnetworks successful and that can make subnetworks operational and give a competitive advantage against what is available today in the 5G era. So we have identified 16 in total technology components within the 6G-SHINE project. We have went forward to identify their possible gains, but also the culprits, both theoretically and practically. The practical part is part of our proof of concept that we are presenting here, and the theoretical part is also being done in the other work packages. So today we have 3 selected proof of concepts that we have available to present to our to demonstrate, and we can go now forward and try to present one of them, each one of them, to our viewers, so they can have more information on our demonstration. Thank you.
Hello, can you introduce yourself?
Hello, I am Christos and I am a telecom engineer.
Great, thank you, Christos. So can you please explain a little bit about what this POC demonstration is about and how is it solving that problem?
Of course, our POC addresses the challenge of interference management in spectrum congested environments like industrial ones. And it does this by distributed power control that relies on message passing granular networks.
Wonderful. Can you walk me through a little bit more into the architecture of your POC demo?
Of course.
Thank you.
We have 2 subnetworks that operate on the same frequency band and thus they interfere with each other. They both run 3GPP compliant protocol stacks, and what we do here is that we have embedded the message passing that is needed on already existing 3GPP signals, which means that no additional signaling overhead is needed. Then, based on the feedback they get from those messages, they decide the transmission power for their data. So they can regulate it and let's say minimize the interference.
Great. So what do you have on the screen? Can you explain that?
Of course, here on the screen we have the 2 subnetworks. The one is dominated by the other. We can see the one that dominates with a green line. So it constantly has a higher rate than the other one. So applying the proposed solution, the team tries to balance the rates and give more power to the dominated subnetwork and also reduce the power of the dominating subnetwork. As a result, we achieve a higher rate, we achieve a higher SIM rate.
Very interesting work, Christos. Thank you. So what's the key message of your demo?
The key message is that we need, for subnetworks, we need distributed, low overhead solutions to manage the interference, and this is what this demo tries to do.
Wonderful. So can you tell a little bit about what are the future steps?
Of course, for future steps, we envision like to also manage cross-technology interference, but also have some over-the-air learning regarding the interference of the environment.
Thank you, Christos. It's great. So let's meet our next fellow here. Hi, can you introduce yourself, please?
Hi, I'm Thijs Haminga and I'm a PhD student at Cogninn University, imec.
Great, thank you. So could you please explain what this POC demonstration is about and how you're solving the problem that you're facing?
Yeah, so this PhD is about cross-technology interference, and we're using Wi-Fi to do this, and specifically ODMA.
Great. Thanks, Thijs. And it would be great if you can walk me through a little bit about the architecture of your POC demonstration.
Okay, yeah, so here we have an open Wi-Fi access point. It's implemented on an FPGA. It is connected to 2 Wi-Fi 6 stations. One is over here, and the other one is over here. Then I create cross-technology interference by these ZigBee transmitters. Those have a smaller bandwidth, but they overlap with the Wi-Fi channel. But since they are only close to this station and not to this station, when they send the feedback to the access point can schedule the OMA resources in such a way that it only does not affect the one that is being interfered.
Thank you. So what's there on the screen? Can you explain the results a bit?
Yeah, so you can see here the throughput of both stations, so orange and blue, and the average in the dotted black line. And you can see in the white area where the scheduler is not active, that one that's being interfered has a decrease in throughput. Whereas in the green area, where we enable the scheduler, both stations can remain at the stable.
Interesting. Thanks. So can you provide the key message of your POC demo?
Yeah, the key message is that cross-technology interference does not have to influence the throughput if we schedule it in the right way.
Certainly. So what are the future steps that you're foreseeing now?
Yeah, so we're trying to make it more scalable to more users and also more different risk management techniques, combining them in one solution.
Awesome. Thank you very much, Thais. Have a great day. So here we have the demonstration on performance evaluation of low latency RIS channel emulation. This is about the work package 2, radio channel measurements and modeling, where we developed a physical model for the reconfiguration intelligent surfaces. That's what was done by our partner, CNIT. Let's have a look at the physical model that was developed by our partner. So this is the macroscopic model that was developed. This is the model that was integrated into ray tracing tool. Here for this demonstration, we are using the focusing lens mode of this macroscopic model, where the RIS is operating as a focusing lens. So the scenario is basically a T-shape indoor corridor scenario. So there is a transmitter that's positioned at the bottom of the corridor, and the user trajectory is moving away from the transmitter from line of sight to the non-line of sight conditions. So the idea is to present how the coverage improves when the RIS is installed and mounted in the environment. So here we see the ray tracing scenario again, but now we see the coverage results at FR1, 3.5 gigahertz, and FR3, 10 gigahertz. The red curves represents the coverage received power with when the RIS is present, and the black curves represent when the RIS is absent. So as the user moves from line of sight to the non-line of sight condition around the corridor, we see that there is clearly coverage gain with the RIS compared to the case when there is no RIS in the scenario. So now you see the animation. So UE is moving from line of sight to the non-line of sight scenario, and how the coverage is behaving with and without the RIS in the scenario. So the blue line is basically the outage threshold, and we see that there is a clear performance gain when the RIS is present in the scenario. Okay, so the next what we did is actually, this is all from the simulations, but what we have done is to demonstrate that in terms of performance evaluation, and we do it. This is POC demo test setup. We have a base station emulator, UXM 5G, and then we have a PropSim channel emulator. Then we have a UE in a shielding box, and where we get the statistics. So it's all done with a test automation platform, and I'm going to demonstrate that to you next. This is just a quick results with and without the RIS. So you see that without the RIS, we have in the line of sight, the throughput is there, but it drops when the user go into the non-line of sight situation. And the same for the with the RIS. So we see that the throughput is maintained all along the RX trajectory from loss to N loss. So let's take a look at the actual demo setup here. So here we have the UXM 5G base station emulator, and then we have a PropSim channel emulator. So the PropSim channel emulator has a channel model embedded with and without the RIS. And what we do, and the UE device is actually available in this shielding box. It's a Faraday cage, so there's an actual UE device which is available inside and it's connected. There's a test PC, and this test PC is controlling all the devices with our test automation platform. So what we do with the test automation platform, we set the 5G cell, all the parameters, run the traffic, load the channel model, respective channel model in the channel emulator, and then perform the test. So first I will show you the test with without the rest. So if you go to the first one, so you see here there's a PDSCH throughput. So when we go from line of sight and then around the corner to the non-line of sight, we see that the throughput drops, and the same happens with the PDSCH MCS. Now, on the other hand, when we have the RIS model or the RIS available in the environment, we see the PDSCH throughput is maintained all along the RX trajectory from the line of sight to the non-line of sight, which clearly demonstrate the performance gain with having the RIS in the scenario. So the key message here is that with the equipment that we have developed within the framework of 6G, which is the low latency channel emulator platform, we are capable of handling advanced use cases that RIS. So the key contributions here is that we have our partner in the 6G-SHINE, CNIT, has developed a physical model for the RIS, which is integrated into ray tracing to generate channel models, and the PropSim low latency PropSim channel emulator platform is capable of handling RIS emulations. So that's the overall message of this POC demonstration.